Welcome again to the Theories of Everything program. I'm David Tao. Viewers, this is the second program in our new series, Theories of Catastrophes, in which we examine the causes and the impacts of catastrophes right from the very beginnings of our planet, right through to the present time, and the potential impact of catastrophes on our civilisation in the future. In our first program, we did a brief flyover of the major categories of catastrophes. We looked at the catastrophes that might occur through events from outer space. For example, the impact of asteroids, meteorites on our planet, which had a large role, in fact, in the early shaping of our planet. We looked at the impact of exploding stars, creation of black holes through supernovas, the release of vast quantities of high-intensity gamma radiation and cosmic particles that can have an effect on our climate, and of course, if they were too close, would lead to the obliteration of a large percentage of our species, including us perhaps. And we also looked at the impact on our climate of passing through dense clouds of molecular dust in our journey around the perimeter of our Milky Way. And also the impact of solar flares closer to home, vast jets of plasma, of ions and electrons and positrons and so forth that are a regular feature of our Sun and have already had impacts on power stations and satellites in our brief history. And then we came to the vast fluxes in climate that have occurred on our planet as it tried to gain equilibrium in its formation. For example, once the densest elements had collected, like iron at the centre of and radioactive elements as well, at the centre of the planet, the outer layers still in molten form, the outer magma, which is mainly made up of basaltic type material, basaltic rocks, formed on top of that the lithosphere or the crust, and they were made up of lighter elements and formed various types of granites from feldspars and so forth. The atmosphere formed from eruptions of volcanoes from deep down in the Earth's mantle, and also the oceans formed again from water vapour and perhaps additional water vapour coming from outside comets. But during this phase, of course, life was struggling to begin as well, and it had an eventual impact on the atmosphere, of course, and on the planet as a whole, which we'll come to in a moment. The planet, of course, went through, again, because of these constant changes and constant evolution, went through vast fluxes of climate change, snowball events, for example, where the whole globe, probably, or most of it, was covered by at least 2 kilometres of ice, and that continued for perhaps millions of years until volcanoes were able to kickstart the reverse cycle, and eventually a sauna situation arose. So you have major changes in climate as well as smaller changes, and of course the last one being the Ice Age that early humans had to endure at its peak in 20,000 years ago. The thaw marking the beginning of our present civilization. So you can see that the planet as a whole has had an enormously turbulent past, coming to terms with itself in the cosmos, but also, if you like, in the form of Gaia, forming its feedback loops, trying to regain equilibrium, and then life kick-starting and it having its impact as well, and it trying to reach its equilibrium and reach its stasis. But there's no such thing as equilibrium in the cosmos. The minute things start to settle down, everything changes again. Of course, viewers, since life emerged approximately 4 billion years ago, it's had a struggle to survive, as we mentioned in the previous program. There have been at least 5 major extinction events caused by asteroid impacts, upwelling of magma, for example, huge increases in carbon dioxide at different times, perhaps changes of going through molecular clouds of dust in the past, or perhaps even impacts from supernovas. In any event, some would say that we're just about to enter our 6th extinction event. And I think we'll have to work very hard and very cooperatively if we're going to survive this one at all. In addition, viewers, since the crustal plates formed, of course, and since civilization began to ramp up, there have been continuing traumas through earthquakes, volcanic events, ocean atmospheric events such as hurricanes and tornadoes and so forth. And the more our civilization continues to grow, the more impact, the greater impact these sorts of events will have. And of course, because of the increasing populations that live in, quite often, that have settled in earthquake-prone areas, areas close to the sea, affected by tornadoes and so forth. So it's been a very difficult process for humans to come to terms with this and understand the causes, and this is absolutely vital that we do understand these causes so that they can be dealt with on a proper basis, and slowly this has been happening. There have been other problems, though, that we alluded to in the previous program, and that is that was brought to our attention starkly during the Indian Ocean tsunami, earthquake and tsunami, in which 300,000 people died and 5 million were displaced. There was a complete communication breakdown between the science community and the general public, and this has still not been adequately addressed, and we'll talk about it again in a future program. And then, of course, we come to the man-made catastrophes, the ones generated by conflict between humans. And this has been with us forever, but of course it's become much more lethal over the past 100 years as the armaments have become much more powerful and lethal in their impact. And as we've come into the nuclear age as well, there's been some very, very precarious moments in our history. And still we are struggling to be able to contain these sorts of conflicts before they get out of hand and before we are obliterated. Also, there's increases of diseases have been with us forever, but again because of population increases, diseases such as malaria are on the increase, and certainly HIV/AIDS, and a number of other potential crossover diseases between animals and humans. So all in all, the scenarios don't look all that promising for humans in the future, but there is a major plus potential, because as the impacts of catastrophes have increased, so has our knowledge of the causes, the understandings, the ability to predict, and hopefully, eventually, the potential to solve them. Viewers, in this program we'll go back to the past again so that we can get a better understanding of the linkages, if you like, between past catastrophic events and the present time, because there is a causal linkage right from the very beginning of this universe, in fact, to the beginnings of Earth and to our present civilization. Everything has a cause and effect, and it ripples through time. If we go back again to the past, to the cosmos, we see that is a huge evolving process. Clouds of gas coalescing to suns passing through the phases of their evolution and finally exploding or diminishing down to a brown dwarf, a white dwarf, the creation of planets, the birth and death of stars, as we commented previously, resulting in huge explosions of particles and radiation, and the formation of heavier elements during that process. I think our sun is a third generation sun, formed from elements from previous times, previous supernovas of two previous generations of suns. And so we have, if you like, the metals in our sun to create as leftovers, as leftover dust, the planets that circle today, and that also on which we live. Because the same chemicals that were born in those supernova explosions and galactic explosions of other types are the ones that are still in our bodies that created us, that created the first cells. So there is continuity there from the birth of the universe to the birth of the Earth, again roughly 4.5 billion years ago. The beginnings of life perhaps 4 billion years ago, a continuity in the elements and structures that formed us. So other events, of course, we had no idea about until quite recently, until the astrophysical sciences, astronomy, astrophysics itself, geology, etc., showed us just what has been going on in the cosmos, the violence of the cosmos. Each star, of course, is a nuclear furnace in itself, and this has the potential to help us solve our energy problems in the future. But in the meantime, we find some strange things going on, indeed. For example, we are part of our Milky Way, our galaxy is part of what is termed the local group, which consists of us, the galaxy Andromeda, and about 30 other much smaller galaxies, dwarf galaxies. That forms the local group. But that group is being drawn to a larger group, the Virgo supercluster, or at probably around about 2 million kilometres per hour. Milky Way and Andromeda are being drawn closer together at around about 500,000 kilometres per hour. And the Virgo supercluster and other superclusters are being drawn towards the so-called Great Attractor. Whatever that is, perhaps it's a black hole at the centre of our galaxy. But either way, we're in constant motion. We're not just sort of planets spinning around and going around our own sun, but our own sun, of course, is hurtling around our galaxy, and our own galaxy is being drawn to other galaxies, which are being drawn to other galaxies, and so it goes. These don't have a huge impact on our existence, but certainly in our travels around the galaxy we do pass through clouds of gas, because the spiral arms of our galaxy move more slowly than we do. So so often we move through these spiral arms, and again the gas, ions, hydrogen, nuclei and so forth have effects. They ionise our atmosphere and they cause molecules to form which reflect solar radiation, so we have cooling periods. Apart from that, we can only hope that we don't get drawn to the Great Attractor in our lifetimes, but eventually humans will have to deal with this if they're still here and if our planet is still here. Of course, our planet won't be here in another 2 or 3 billion years, because by that time the sun will have burnt its primary energy of hydrogen, converted it to helium, converted it and will expand greatly and just encompass all the planets, which will be basically burnt to cinders. So hopefully within 2 or 3 billion years we'll have gone to another galaxy, another star, another planet. And if that wasn't enough, we have to contend with other major events that again produce huge bursts of gamma radiation, cosmic particles. These cosmic particles, by the way, that rain down on our planet, and we're only protected from them by the atmosphere, cause multiple sort of ripple-on collisions. Their impact can be as high, they move at relativistic speeds, almost the speed of light in some cases, and they literally have, these protons have the impact of a golf ball driven by Tiger Wood. That's the potential energy, the kinetic energy in some of these cosmic particles, so great is their speed. But again, our atmosphere protects us, and it protects us also to a certain extent from again the solar flares, the huge plasma jets that are radiated out and probably caused through various magnetic electric fields within the sun itself, convection currents within the sun, and these huge magnetic loops of plasma explode out every now and again and can directly cause us damage, and have done so again, knocking out satellite communications power plants back, I think, in '87, major blackouts. So we're not immune from these space events. And of course, if a supernova itself is close enough, if it's closer than say 200 million light years, it can do us extreme damage. certainly as we move into the space age, our astronauts will have to be extremely careful and well protected, and all space ships, space stations will have to have very thick skins to protect against cosmic particles. There's enough particles to shred an astronaut's DNA very quickly, and enough radiation as well. I think about 80 rems of radiation. The normal maximum for a nuclear worker should be about 5 rems a year, but once out beyond our protective atmosphere and magnetosphere, the magnetic field of the Earth, which also provides some protection, then we would feel the full impact of these types of radiation, which destroy it. Viewers, we could continue to talk on and on about the cataclysmic events that occur in the universe, close to us or distant from us. Regardless, they have some form of impact. And again, we were born out of this particular universe, out of the particular cataclysmic events that have occurred, including the birth and death of stars, again, the constant evolution of regathering of dust for new stars, new generations of stars, leftover dust in the form of metals, that's heavier elements, that eventually ended up as little planetesimals, little 10-kilometre across pieces of collected debris under the force of gravity, and eventually they formed the rocky planets, on one of which we exist and have survived. It's interesting to note, though, that if any of those events that first of all created our third generation sun and then allowed the planets to form, and we just happened to be in a convenient place the right distance from the sun, so that the right amount of warmth and stability was provided in the right sort of orbit with the right sort of combination of other planets around, so that some of the meteorites, for example, that could have completely obliterated us were deflected by Jupiter, for example. If any of these events since the beginning of the universe had not occurred the way they have, then we on this planet would not exist. We may have existed on many other planets, though, or life may have existed and kick-started in roughly the same way. But in our particular planet, all these different combinations of events created us. And paramount in this process was the formation of the crust of our Earth. As mentioned, at the core of our Earth, the heavier elements formed there. In fact, the core is a huge molten iron dynamo with an inner core and an outer core with a radius of about 3,000 kilometres. And because of the spinning of the Earth, that creates a dynamo effect, Coriolis effect it's called. And also it's a electrically and magnetically conducting mass. So that creates our own magnetic field, 1% of which only is felt on the surface. And that can flip because of complex convection currents working in that inner core. Every now and again that flips, and quite regularly it does, as can be measured by the magnetic polarisation of the sediments of the Earth. Now, on top of that is formed the molten basalt material, very dense material, and that continues to bubble up and create volcanic events. On top of that, again, our crust of lighter elements is formed, about 10 kilometres, 20 kilometres thick. And that was quite crucial to life, because life needed something to gain a foothold on, in the form of, particularly in the form of animal life. Early animal life was born into the seas. Early fishes, of course, migrated then in the form of tetrapod fishes. The fins became little limbs, and they were able to crawl up onto the land. Gills became lungs, but this was a slow transition process, but it happened around about... The crust was formed from lighter elements, silicon-based, calcium-based elements, that were able to interact with the atmosphere, the carbon dioxide primarily in the atmosphere, through a process of weathering, and to absorb that carbon dioxide in the form of, for example, calcium carbonates. And gradually that led in the early formation of the Earth to a cooling effect. As the carbon dioxide was dragged out, also ice started to form, and then in kicked the albedo effect, which is reflection of light and heat from the surface, a white surface. And then that led to a positive feedback effect, which increased the surface area of the ice, less carbon dioxide again, and gradually you entered into that snowball process, a snowball period, when temperatures dived to around about minus 50 degrees centigrade. There were a few hot spots though, hydrothermal areas under the ocean, and also perhaps a few on land, that kept life going in the form of early algae, single-celled organisms, and over time, as mentioned, the volcanic effects, the rising of magma from the and basalt through the ocean floors and through the land masses, gradually created more carbon dioxide and reversed that process. At the end of the last snowball event, life really kick-started. The first animals, first tiny worms evolved, probably around about 600 million years ago. And of course the atmosphere had changed also, because early plants, early algae, early lichens had learnt had evolved, if you like, the benefits of photosynthesis, to use the energy of the sun together with water to convert carbon dioxide into more complex sugars and their requirements for growth, more complex molecules, so that basically then oxygen became and produced oxygen as a side product, and that became a much more major component of the atmosphere, and that was able to be utilised by the early animals. Early blue-green algae, of course, has been found, discovered in West Australia, for example, in early stromatolite mounds going back 3.5 billion years and even further. But there was a huge shift at that time, multicellular organisms, at the end of that last snowball effect, and life really got underway. The crust, though, is again quite critical in relation to catastrophes, because obviously that huge mass of crust around the equator continued to move, because remember it's on a fairly thin layer, and it broke up at various times. Around 150 million years ago there was a mass called Pangaea. It's been named, and that broke into several parts, including Gondwana, and that broke again further around about 125 million years ago into an Indian mass, and all these plates started to gradually shift and move and realign themselves, and that formed the basis of the science that we know today as plate tectonics. There's seven major plates that today: the Indo-Australian plate, the North and South American plates, the Antarctic plates, the Pacific plate, and a number of smaller plates as well. And these, of course, are responsible, the movement of these plates are responsible for all the earthquakes and volcanic events, and including follow-on events such as tsunamis that we know today, and have created most of the catastrophes for humans. So now, viewers, the stage is set. All the players are in place. All the stakeholders are in place. Plants have established themselves. Animals have established themselves and are evolving. All are constantly moving through various ecosystem phases. All the different climates have started to evolve, driven by the ocean currents, driven by the atmosphere. The atmosphere is now a combination of carbon dioxide and oxygen, and nitrogen, of course, and various other small numbers of elements. Basically, everything's come into this sort of quasi-equilibrium, but as we said before, there is no real constant equilibrium. But the players are all set. Humans have evolved to the point, let's say, over the last, since they're split from primates about 7 million years ago, they've evolved greater intelligence. Modern humans have evolved around, say, 140, 150,000 years ago and are beginning to explore the Earth as their forebears did before them, early Homo erectus, etc. But now they're at the point where they have to begin to understand these catastrophes. This is the point at which early myths were derived, to try to understand when these huge fiery volcanoes burst forth and the land rumbled underneath them. They had to invent a reason for it. They invented gods, basically. They invented spirits. They tried to get their minds around these huge events that entangled them. So the stage is set for them to begin this long journey to understand and deal with the catastrophes that are about to befall them in the future of the planet and the future of their universe. I'm David Tao, and you've been watching the Theories of Everything program again. I'll look forward to seeing you again next week.